Alright, so let's start off this electricity and magnetism course with electrostatics. Okay, so electrostatics, simply as the name implies, we're talking about electrons or charged particles that are not moving, statics. So I recommend that you read section 1 of chapter 22 right away. It gives you a lot of good visual representations of some of the experiments that are going on. Okay, so let's start with electric charge. Okay, and there are two basic fundamental types. Okay, this is something you probably learned in chemistry. You've got your protons and electrons. So when we're writing a proton as a variable, we'll typically use lowercase e with a positive superscript, and an electron would be a e with a negative superscript. Okay, and these two things are considered the fundamental charges of nature. In other words, nothing gets smaller than this. Now, of course, if you look a little bit ahead and go into subatomic physics, then you will see that, well, protons are made up of other entities, and so there's things that give proton its charge, but every form of matter is made up of protons, so we consider protons and electrons to be the fundamentals. Okay, but this also means that charge is a quantized thing. In other words, you can never have a charge that is a fractional amount of protons or electrons. Okay, so the amount of net charge an object has is simply a sum between the protons and the electrons, and then times the charge unit. Okay. So if we say that a charge is equal to 0, okay, this does not mean there's no charge. It means that there's no net charge. Okay, and that's important because saying that there's no charge means that there is no proton or electron in the object, and that's just not true. Every form of matter is made up of protons and electrons. Okay, so that's identifying charges. Now the question is, well, how do we get charges? How do we get them to build up on an object and give us a net charge? Okay, so in order to acquire charge, okay, there's a few processes in doing this. But first we need to understand exactly what it is that's moving in terms of charges. Okay, so for example, let's say an object becomes positively charged. Okay, so what does this mean? Well, if an object becomes positively charged, okay, some students might immediately say that it must have gained protons, but that's simply not true. Okay, there's no way that an object can gain protons, because think of back to chemistry in the periodic table. If you gain protons, you become a different element entirely. Same thing about losing protons. You can't lose them because then you just become a different element. So in order to become positively charged, that essentially means that you lost electrons. Okay, and in chemistry you learned this as the term ionization. Okay. So this brings us to another idea referred to as a conservation of charge. Okay, and like the law of conservation of energy, conservation of charge simply states that electric charges cannot be created or destroyed. Okay, all we can do is redistribute them between objects. Okay, so consider two objects. Let's say object 1. And let's say that object 1 becomes negatively charged. Okay, in order for it to become negatively charged, it must have gained electrons. All right, but where did those electrons come from? We can't create them, so they had to have come from somewhere. So in order for object 1 to become negatively charged, there must be another object, call it object 2, that lost those electrons. And by losing those electrons, this object actually became positively charged. Okay, but overall, the system containing these two objects, overall the net charge is still 0. Okay, there's still the same amount of electrons and the same amount of protons that we started with, assuming both objects were neutral to begin with. Okay, so one of the things then too about transferring charges is we need to know what types of materials we're dealing with. And the book uses or constantly refers to like plastic and glass and metals. Okay, so why is this important? Well, the book uses these specific materials. They're really outlining two basic types. Okay, and those are conductors and insulators. Now, conductors are materials that allow electrons to move freely. Whereas insulators, you can think of it as the charges are glued or fixed in place. Okay, so the question then becomes, well, how do you charge an object? How do you actually get charges to get to another object? Okay, and well, conductors are easy. If you give the electrons a path, they will move because the conductors allow electrons to move. Now, the real challenge is insulators. So insulators must be charged by a rubbing or friction. Okay, that action, that energy helps to rip apart the electron or the atoms by tearing the electrons off of the nuclei and attaching them to the insulators. So when the electrons are added to conductors, they repel one another and they will spread out until there is no net force on them. This is known as electrostatic equilibrium. Okay, and an isolated conductor in electrostatic equilibrium has all of its excess electrons located on its surface. And that's an important idea, especially when we start talking about electric fields and things like that. All right, so how do you discharge an object? Well, again, a conductor is easy. To discharge a conductor, all I need to do is connect it to another conductor, which effectively forms a larger conductor, and then charge will then spread out until it's in equilibrium. And then when I separate those objects, the original conductor will now be discharged. Okay, and this brings us to another point. It's something we refer to as grounded. It's more common in electrical circuits. And grounded literally means that you take a conducting path like a wire and you connect it deep into the earth, into the ground. The earth is so big that all of this excess charge drains off of your conductor and spreads out through the entire volume of the earth. Okay, and so that helps in electric circuits, and so that excess charge doesn't build up in your circuit. Okay, now polarization is another way you can gain charge. So in this example, consider an insulator, a rod, that's filled with electrons. So it's got a net negative charge, and we bring it to a conducting circle or sphere that's neutral. Okay, so what I'm going to do is we're going to take this insulating rod and we're going to put it close to this conducting material. Okay, the important thing is we don't want to touch it. So if we take this rod, bring it in close, but it's not touching. Okay, what the negative charges on the rod are going to do is they're going to force the electrons that are on this conducting sphere to move as far away from the rod as possible. Okay, because as we know, like charges repel and opposite charges attract. So the protons are stuck in place. Okay, the atoms themselves are not moving around in the material, just their excess electrons. So you can see all these electrons will get as far away as possible until they're in equilibrium. And what this effectively does is it takes this neutral object and splits it into two different charges. One side is slightly positive, the other side is slightly negative. Okay. Now, of course, once we bring the insulating rod and we take it away from this conducting sphere, the charges will redistribute pretty instantaneously, and then the sphere itself will become neutral once again. Okay. Now, another form of charging is what we refer to as induction. So induction works a lot like polarization, except we want to maintain the charge we've established on our conductor. So we're going to do a similar setup. We're going to take a insulating rod that's negatively charged, okay, and then we're going to bring it close to a conductor that's touching another conductor. So imagine two conductors that are touching, and so effectively you've got one large conductor. And you can see by the pluses and minuses that overall the two objects together are neutral. Right? There's a total of 8 positive charges and 8 electrons. Okay, so now we're going to do like we did with polarization. We're going to bring that insulating rod close to this conductor. Okay, and then the same thing is going to happen. Because this rod is negatively charged, all of the electrons on the closest part of the conductor are going to try and move as far away as possible. But rather than just moving to the other side of the sphere, it's connected to another conductor, so there's a path. So all of these electrons are then able to then dump themselves, or most of them anyways, are going to dump themselves onto the other object, the one that's outlined in blue. Okay, now if I take the insulating rod away, well, these electrons will redistribute and we're back to being both neutral. So instead, what we're going to do first is take the blue conductor and move that one away. Okay, and then when we do that, you now have one of these conducting spheres, which was originally neutral, now has a positive charge, and the other one has a negative charge. And since we've disconnected the path, those charges will stay exactly where they are on those spheres. And so without even touching the object, we've effectively created a charge. And notice that we actually charged the black sphere, which was closest to the rod. We charged that one to an opposite charge of what the rod was. Right? We bring in the rod, which was negatively charged, and as a result of charging by induction, the black conductor became opposite, positive charged, and the blue conductor became negatively charged.